Welcome back, Cat 5 class. Today we're going to be covering Chapter 13, Tolerancing, no AutoCAD. Chapter 14 will cover tolerancing using AutoCAD. So what is tolerancing? Think of tolerancing as wiggle room. So if you go to the supermarket and you're going to get a pound of a certain fruit, hey, let's say you're going to get 2 pounds of a certain fruit or vegetable that you like, but it's hard to hit that exact 2 pounds, so there's going to be what's called tolerancing, or think of it as wiggle room. Okay, as long as somewhere near 2 pounds plus or minus, 2 ounces, for example. So once again, think of tolerancing as wiggle room. Next slide. Tolerancing and interchangeability. Tolerancing is dimensioning for interchangeability. What is interchangeability? An interchangeable part is simply a mass-produced part, a replacement part. Interchangeability, perfect example is replacing a part on your vehicle. So if something breaks down in your vehicle, you can either take it to a local shop or you can go to an auto parts store and order the part yourself or purchase the part online. Simple example is replacing an old water pump on a vehicle, replacing a pulley, or replacing a belt on your vehicle. Here's another example, replacing a fan clutch or maybe a simple bushing that goes inside the hole, or replacing some of the electrical on your vehicle. Side mirror, for example, you can order at the dealership, maybe replacing a radiator. So again, these are parts that are mass produced for interchangeability. Something breaks down in your vehicle, go to your local auto parts stores, dealership, order the parts on your own, and replace the part yourself. And these parts are mass produced to keep it affordable. And when you mass produce a water pump, fan clutch, or any part, you need to give the manufacturer some wiggle room as to how far off they can be. Simple example, this simple bronze, or it can be copper bushing. If you ask the manufacturer that you need this outer diameter to be 1 inch, for example, you have to give them some wiggle room as to how far off they can be. You can, for example, tell them as long as the diameter is within 1.001 and 0.999 inches in diameter, then it's acceptable. So again, you mass produce parts, but you have to give the manufacturer some wiggle room as to how far off how much they can be off by, and yet make it acceptable to replace an old part on the vehicle, for example. Next slide. How is a feature on an interchangeable part dimension? The feature is not dimensioned using a single value, but a range of values. So when you go into a machine shop and you ask them to make you a bushing of bronze or copper, and you ask them for a diameter of 1.00 inches, the shop is going to ask you for tolerance. The tolerance is how much can they be off by. So you're going to give them a range. You're going to tell them, hey, as long as the diameter is not above 1.005 inches, and as long as the diameter is not below 0.994 inches, then you'll accept the part. And this is referred to as the tolerancing. So how much can you be off by? You cannot ask for a perfect 1.00 inch diameter part. It's impossible. The machines that make the part, whether it's a lathe or you machine it with the 3-axis Fadal, they're not perfect, nor are the measuring instruments. Measuring tape, a set of calipers, or a ruler is not perfect either. So there's no such thing as a part with the perfect length or diameter. There's always going to be something slightly off. So we need to provide a tolerance, which is how much can you be off by. Next slide. A tolerance is the amount of size variation permitted. You can choose a tolerance that specifies a large or small variation. So once again, going to the previous example, you're telling the machine shop, I want a diameter of 1.005 to 0.994 inches. Anything in between will also work, as long as it doesn't go beyond the 1.005 or below the 0.994 inches in diameter. So the tolerance is the difference. So all you have to do is subtract 1.005 minus the low, 0.994, and that's 0.011 inches. So this is the tolerance. This is how much wiggle room you're giving the machine shop. Yes, you are aiming for 1.00 inches in diameter, and you're given the machine shop a tolerance of 0.011. 5 in one direction, 6 in the other direction for a total of 0.011. So once again, you're giving them a 0.005 in one direction minus 0.006 in the other direction, and that's how we get 0.994 for a total of 0.011 in tolerance. That's how much wiggle room you're providing for the machine shop. Next slide. Why do we want parts size to be controlled by two limits? It is necessary because it is impossible to manufacture parts without some variation. And as mentioned before, there's no such thing as a perfect part with the perfect desired dimensions. The stated limits are a form of quality control. So the quality department will be checking the parts to make sure they fall within that tolerance. If it doesn't, then the part will have to be rejected. Next slide. Choosing the correct tolerance for a particular application depends on the design intent and use of the part. How is the part going to mate with other parts? What is the function of the part? What is the cost? How is it manufactured? Is it machined? Is it welded? Is it a combination? Is it 3D printed? And also based on your experience. Next slide. The tolerancing methods presented on a drawing are the following: limit dimensions, plus or minus tolerances, or page or block tolerances. Let's take a look at each one. Limits are the maximum and minimum size that a part can obtain and still pass inspection. So for example, the diameter of a shaft might be specified as follows. Maximum acceptable diameter for a shaft, diameter 1.001 will be the maximum. The minimum allowed is 0.999 inches in diameter. Obviously, we're aiming for a 1-inch diameter. It's right in between both. We're aiming for a 1-inch diameter, but we'll accept a maximum of 1.001, and we'll accept a minimum of 0.999. If you take that shaft and it measures 0.998, then it falls out of our accepted tolerance and it'll have to be rejected. If we have a diameter of 1.002, which is more than our maximum allowed, then we have to reject it. Only shafts that fall in this range, maximum 1.001 to a minimum of 0.999 inches, and anything in between is acceptable. Again, the desired size is a diameter of 1.00, but you have to give the machine shop some wiggle room. And again, this is the way we list limits. We just list the max and the minimum in a vertical fashion, the max on top, minimum on the bottom. Or you can also do it horizontally, but you call out the minimum first and the maximum second. So you're saying diameter acceptable from 0.999 up to 1.001 in diameter. Next slide. On the previous slide, we talked about providing a tolerance of max and minimum. In this case, we're going to call out the dimension with a plus or minus tolerance. Plus or minus tolerances give a basic size and the variation that can occur around that basic size. So our desired, let's say length, in this case, let's say it's a length of 10 inches. That's our basic size. On the previous slide, it was a diameter of 1 inch. That was our basic size. That's what we're aiming for. So our basic size here is length of 10 inches, let's say. And the machine shop is going to ask you for a tolerance. How much can they be off by? So you're going to tell them, okay, you can be on the heavy side, or I should say the longer side, of plus 0.1. So if you add plus 0.1 to the 10, That means the maximum length you'll accept is 10.1. And they're going to ask for a minimum. What's the minimum length that you will accept? And they're saying you can be off by minus 0.2. So it's just 10 minus 0.2, which is 9.8. So here the machine shop knows as long as the length of the item is 9.8 up to 10.1, it's acceptable. Anything beyond that would be rejected. So once again, this is providing the basic size of 10. This is the desired size. And the plus or minus, you're telling how much wiggle room you're giving the machine shop. Next slide. Page or block tolerances. A page tolerance is actually a general note that applies to all dimensions not covered by some other tolerancing type. So in other words, if a machine shop is looking at your drawing and they see a length of 1.00 inches, for example, but you don't provide a tolerance. If you don't provide a tolerance, how much they can be off by, then what they'll do is they'll look in the title block. And this is very common. You'll see this note in a title block. So the machine shop, they'll look at your dimension. Let's say you have 1.00. That's 2 decimal places. So they'll go to this note. They know they can be off by plus or minus 0.010. If your dimension is 1.000, 3 decimal places, then they'll apply a tighter tolerance of 0.005 inches, which is about the thickness of a hair. If you want a tighter tolerance, a more accurate dimension, then you go with 4 decimal places, 1.0000 plus or minus 0.002 inches will be the tolerance. It's a lot tighter tolerance. This is about half the thickness of a hair. So once again, if you call out a dimension with no tolerance, then the machine shop will just read the number of decimal places and apply the tolerance listed in the title block. So this is something that you'll see on actual drawings as opposed to the previous slide. These are the tolerances that are most common when dealing with the drawing that uses inches as its units. And just to give you a reference, a human hair has a thickness of about 0.004 inches. A sheet of paper has a thickness of about 0.004 inches. A credit card or ID has a thickness of about 0.030 inches. And a compact disc, like a music CD, has a thickness of about 0.050 inches. So once again, if you give a length of, let's say, 1 inch, and it's only 1 decimal place, in other words, it's 1.0 inches, you're telling the machine shop to go into the title block, and they'll look at the title block. Again, you're not providing a tolerance directly on the dimensions, so they have to look in the title block, and they'll say, okay, 1.0, 1 decimal place, then we can be off by plus or minus 0.1 inches. And 0.1 inch is about 2 compact discs stacked together. So that's how much you're telling them they can be off by in each direction. So you're telling the machine shop it's going to be plus 0.1 minus 0.1. So add and then subtract 0.1 from 1 inch, and that'll give us anywhere from 1.1 down to 0.9 inches. So that's how much they can be off by. If you list a dimension of 1.00 and you don't call out the tolerance, then once again, the machine shop will look in the title block, look at 2 decimal places, 1.00, and now you're telling them they can be off by plus or minus 0.030. And that's the thickness of a credit card. So your tolerance or your wiggle room is a lot tighter. You're giving them less wiggle room. And 2 decimal places is the most common dimension you'll see. So when you're creating a drawing and you start throwing in dimensions and you don't know how many decimal places to start with, always start with 2 decimal places. If you need more accuracy, like the diameter of a hole, for example, then you can go with 3 decimal places. And you can say 1.000, and that'll tell the machine shop that they can be off by plus or minus 0.10 thousandths, which is about 2 human hairs in each direction. Okay, so this is very common to see on a hole that needs accuracy. 2 decimal places is the most common that you'll see on a drawing. 1 decimal place, not very common. It's something that you'll see on large objects where the length is not that important. And you can tell them they can be off by 0.1 inches in either direction. Next slide. Okay, let's review some terminology. Once again, limits. When you provide the limits, you're providing the maximum allowed and the minimum allowed. So maximum, once again, a good example is 1.1 and the minimum 0.9. So those are limits. Basic size. The basic size is the size from which the limits are calculated. So basic size is what you're aiming for. So 1 inch diameter is a good example of a basic size. It's what you're aiming for, and you're going to give them a tolerance, in other words, a wiggle room of how much they can be off by. When it comes to dimensioning the diameter of a hole or a shaft, you typically go with the closest fraction. So a common diameter for a shaft or for a dowel pin can be a 1 inch, half inch, quarter inch, eighth inch, 1/16 inch diameter, 7/16, 31/32. So what you commonly see on a ruler. Tolerance is the total amount. Specified dimensions is permitted to vary. That's your wiggle room. To practice tolerancing, we're going to take a look at something that's very common on a drawing, and that is hole patterns and hardware. So typically where you have a hole, you'll have some type of hardware that goes through it, whether it's a shaft, a dowel pin, or a screw or bolt. Okay, so we're going to use these as examples to practice tolerancing. Okay, let's take a look at the shaft first. So the shaft, the maximum allowable diameter allowed is 0.51. That's our max. And 0.47 is our minimum. So those are our limits. 0.47 up to 0.51 in diameter for the shaft. And now let's take a look at the hole. The maximum hole allowed is 0.50 and the minimum is 0.49. So again, minimum 0.49 up to 0.50 in diameter for the hole. When you call out limits vertically, you put the max on top, minimum on the bottom, max on top, minimum on the bottom. When you call it out horizontally, you call out the minimum first and then the max. Okay, so now that we called out our limits for the shaft and the hole, what is our basic size? So what is the diameter that we're actually aiming for? And that should be pretty simple. It's 0.50, or if we convert it to a fraction, half inch. Okay, so it's obvious if you were to round this off to a nice fraction, half an inch would be the number we're aiming for, or 0.5 or 0.50. So that's our basic size. That's the number we are aiming for. Okay, now the tolerance. That's the wiggle room. So for the shaft, the wiggle room you are giving the machine shop, we are aiming for a 0.50 diameter, and the wiggle room that we're giving them is 0.04. What we have to do is subtract 0.47 from 0.51, and our tolerance is 0.04. So the basic size we're aiming for is half-inch diameter, and we're giving the machine shop a wiggle room of 0.04, 0.1 in one direction, 0.003 in the opposite direction, for a total of 0.04. And for the hole, we're giving them a tolerance or wiggle room of 0.01, so we just subtract 0.49 from 0.50 and we get 0.01. That's the wiggle room we are providing to the machine shop for the hole diameter. So here we're basically telling the machine shop, yeah, we are aiming for a 0.50 or half-inch diameter, but 0.50 is the max. But on the low end, you can be off by 0.01. We can be off by as low as 0.49 in diameter, but the maximum acceptable is 0.50. We cannot go beyond 0.50 in this case. Next slide. A very common term you're going to hear in manufacturing, automotive, aerospace, you're going to see it a lot on drawings, is maximum material condition, or the MMC. This is also covered in a GD&T class, Geometric Dimensioning and Tolerancing class. We're not going to cover it that much in this class other than this chapter and the next chapter, but this is a very common term. You'll hear this term a lot in the GD&T class. Okay, maximum material condition, MMC. The MMC is the size of the part when it consists of the most material. Least material condition, or the LMC. The LMC is the size of the part when it consists of the least material. So the MMC is the maximum material allowed to make it acceptable, and the LMC is the least material condition acceptable. So let's take a look at the shaft and the hole and discuss MMC and LMC for each one. Okay, let's first look at the maximum material condition for the shaft. Okay, so when will the shaft be at its maximum material? That's when it has the most material. In other words, it's when it's at its heaviest. So it's when it has a diameter of 0.51. So that's the maximum diameter allowed. That's where it'll be at its most material and at its heaviest. Okay, now let's take a look at the maximum material for the hole. So here it's the reverse. It's not 0.50. Its maximum material will be at 0.49. So here we're not actually looking at the hole, we're looking at the block. So we have a block. We drill a hole. We'll have more material left over when you drill the small diameter hole allowed, which is 0.49. If you were to drill up to a 0.50 diameter, then you're removing more material. So that's when you have less material, when you drill at the maximum diameter. When you drill with the smallest diameter hole allowed, then you leave behind more material. So the maximum material for this block, or when it's at its heaviest, it's when you're dealing with the smallest diameter allowed of 0.49. Okay, let's look at the LMC, the least material condition for the shaft. Obviously, it's when it's at its smallest diameter. So at 0.47, we'll have a smaller, narrower shaft. It'll have the least material condition. It's when it's also at its lightest. And obviously for the block, we'll have less material when we drill the largest diameter hole allowed. So the larger the hole, the more material you're removing, and you're left with less material in the block. Okay, so the LMC, least material condition for the block, is when you drill at the maximum allowed diameter. So it's just the reverse when it comes to the shaft and the hole. The larger the diameter on the shaft, the maximum material. The smaller hole, the maximum material in the block. Okay, next slide. Let's take a look at the relationship between the hole and the shaft. Maximum clearance. The maximum amount of space that can exist between the hole and the shaft. If we want to achieve the maximum clearance between the hole and the shaft, then we have to take the least material condition hole allowed minus the least material condition of the shaft. Next slide. Minimum clearance. The minimum amount of space that can exist between the hole and the shaft is just maximum material condition of the hole minus maximum material condition of the shaft. Let's take a look at some visuals. Okay, so looking at the two previous slides, once again, maximum clearance is the LMC, the least material condition of the hole, minus the least material condition of the shaft. In other words, it's just the largest hole, diameter hole allowed, minus the smallest diameter pin allowed. If you insert this small pin inside the large hole, there will be plenty of clearance between the two. Now the minimum clearance will be when you have the MMC, the maximum material condition for the block, minus the maximum material condition for the shaft. In other words, it's just a small hole, the smallest hole allowed, minus the largest diameter shaft allowed. And obviously, you can see there's a lot less clearance than the max clearance. Here we'll have less clearance between a large diameter shaft and the hole versus the small diameter and the large hole. Here we'll have more clearance, here we'll have less clearance. The minimum clearance, maximum clearance. Next slide. So what is the maximum clearance you'll find between this shaft and this hole? So all you have to do is take the largest hole, 0.50, and subtract the smallest shaft allowed of 0.47. Okay, so once again, the largest hole allowed, 0.50 diameter. The smallest shaft, 0.47. The small shaft and the largest hole will have a clearance of 0.03 inches. That's the maximum clearance between these two. What's the minimum clearance? It's just the opposite. It's the small hole of 0.49 minus the largest diameter. So in this case, we'll have actually a larger shaft than the hole. So we'll have to hammer this pin into the hole to make it fit. So we'll end up with a negative clearance, minus 0.02. Why? Because the hole is smaller than the shaft. So you'll actually have to take a hammer or a mallet and pound it into the hole. Okay, so we end up with a negative clearance, meaning it's clashing. Next slide. What does a negative clearance mean again? So once again, we have a minimum clearance of negative 0.02. In other words, the shaft is larger than the hole. So you won't simply be able to insert the shaft into the hole. You will need to force it in there with a mallet or a hammer, causing a clash, and friction will hold the pin in place. Next slide. So when you have the shafts manufactured, mass production, and the blocks with the hole also mass produced, you're going to end up with one of the following relationships between the shafts and the holes. Again, we're talking about interchangeability. You don't know if you're going to end up with the larger diameter allowed or the smallest diameter allowed. So when dealing with interchangeability, you're going to have one of the following four relationships between the shafts and the hole. You're either going to end up with a clearance fit, an interference fit, a transition fit, or a line fit. Clearance fit. So clearance fit always guarantees a space between the shaft and the hole. So when you do your calculations for your max clearance and your minimum clearance, you'll always end up with a positive clearance for max and minimum. Okay, so a good example of clearance fit is when you simply have a bolt going through a hole, not engaging with threads, but just a bolt going through a hole. The hole is always larger. You should be able to fit a credit card between the hole, the clearance hole, and the bolt, which is about 0.030 thousand inches of clearance. So if you have a machine shop make you a bucket of bolts and a bucket of blocks with holes, The screw or the bolt will always go through freely with always providing you with space, always with the clearance, plus maximum and plus for the minimum. Next slide. Interference fit relationship. It's the opposite of clearance. It's when you'll never have a space. So in this case, when the machine shop makes a bucket of, let's say, dowel pins or shafts made out of steel and blocks made out of aluminum with holes, in this case, you're always guaranteeing that the hole is always smaller. So you will always end up with a maximum and minimum clearance of negative. The hole will always be smaller, so you would have to force the dowel pin or the shaft into the hole either with a mallet, a hammer, or you may have to hydraulically or use a press to push the pin into the small hole. Next slide. Transition fit. This is a rare occurrence, but in the transition fit is where you may end up with space or no space. So in this case, this is where you have a positive maximum clearance and a negative minimum clearance. So in this case, when you have a bucket full of shafts and a bucket full of blocks with holes, and in this case, as long as they both are within the tolerance provided by the drawing, in this case, if you randomly pick a shaft out of the bucket and a block with a hole randomly out of the other bucket, and you place it inside, you don't know if you're going to end up with space or no space. Either you'll freely be able to insert the shaft in the hole, or you're going to have to force it in there with a hammer or mallet or with the press in case the hole is smaller. So in this case, you may end up with a larger hole or smaller hole in relationship to the shaft. Next slide. Line fit are also referred to as an inline fit. In other words, that there's either going to be a space or a perfect contact, meaning the hole and shaft diameter are equal. Think of it as a hand to a glove, the perfect glove for your hand. So in other words, if you take a shaft out of the bucket and a block with the hole from the other bucket, you're either going to end up with the perfect match where the diameters are exactly the same, where you can just simply push the shaft into the hole and it'll give you a perfect relationship because they both have the same diameter, or there's just a little bit of space so you can still push the shaft into the hole, but clearly you'll see a little bit of space and a little bit of wiggle room. Next slide. So let's take a look at clearance once again. The clearance relationship is when you take the large hole minus the small shaft and you end up with a positive clearance. And your minimum clearance, you take the small hole minus the large shaft and you also end up with a positive. So clearance guarantees there's always space between the shaft and the hole, and you'll know because you'll get two positives. Positive for your max, positive for your minimum clearance. Now let's take a look at transition. Transition is when you have a maximum clearance that's positive, but for the minimum clearance, you end up with a negative. Small hole minus large shaft will give you a negative. So in other words, the hole may end up larger than the shaft or smaller than the shaft. So this is referred to as transition. You'll end up with a positive clearance and a negative clearance. So you may end up with either or. If you randomly pick a shaft from the bucket and a block from the other bucket, randomly pick one, you may end up with a large hole or a small hole, either creating clearance or interference. Okay, interference is when you have both negatives. That tells us when you do the maximum clearance calculation and the minimum clearance calculation, you're going to end up negative for each one. So that guarantees interference no matter what. So anytime you pick a random shaft from the bucket and a block with the hole from the bucket, the hole will always be smaller, always guaranteeing an interference, meaning you have to take the shaft and force it into the hole with the hammer or a press. And finally, the inline fit is when you have a perfect match. So your maximum clearance will always be positive, always guaranteeing a clearance, or a perfect fit, the minimum clearance will be 0. Not a negative, not a positive, but 0. In other words, the diameter of the hole and the shaft are exactly the same. So this is once again hand to a glove. It's a perfect match. Either the shaft fits in perfectly because they have the same diameter, or the hole is just slightly larger, providing a little bit of wiggle room. Next slide. So where do you see clearance in the real world? So a good example is when you open the door to your house, you insert the key. The key is always smaller than the keyhole. So the lock has the keyhole and the hole will always be larger than the key. We always want clearance. We don't want a key that's larger or else we won't be able to insert the key into the keyhole. Another example is a door. When you open the door, you want the door to be slightly smaller than the door frame. The door frame is the hole. You don't want a door that's larger or else it'll get jammed in the door frame. Another good example is a coin to a slot. You always want the slot to be larger than the coin, so there's always guaranteed clearance in these items. Where do you see interference? Good example of interference is a bicycle chain. The pins and the bicycle chain have a slightly larger diameter than the holes that they are inserted in. Another good example are the hinges on a door, for example. The pin is just slightly larger. You don't want the pin to slip out of the hole or the holes in the hinges. So here's another good example. The pin is always larger than the holes in the hinges. Another good example is also a wooden peg and a hammer toy. There's always interference. The hole is always smaller. Once again, interference example. The pins on a bicycle chain are just slightly larger in diameter than the holes, or else the pins will slip out. Same thing with the pin. You want the pin to just be slightly larger in diameter than the holes in the hinges. You don't want the pin to slip out, or you don't want the door where this hinge is attached to be wiggling because the pin is slightly smaller than the hole. We want the opposite. We want the pin to just be a little bit larger than the hole, so we have to force the pin into the holes by friction. In other words, there's no clearance, there's interference. All right, so let's take a look at some examples. This is what you're going to be doing in your assignment. You're going to be looking at the relationship between the shaft and the hole. Okay, so let's take a look at a shaft. Here are the limits. So this is what's allowed for the diameter of the shaft. So 1.498 is the minimum diameter. 1.500 is the max, and anything in between is acceptable. And this shaft is to be inserted into a hole with a minimum diameter of 1.503 up to 1.505 for our maximum diameter. Okay, so what's the basic size? Take a nice round fraction. Obviously 1.5 or 1.5 is our basic size. That's what we're aiming for. So if you were to round this off to 1 decimal place, we would get 1.5. Now, what type of fit are we going to get between the shaft and the hole? Well, since the hole obviously is larger than the shaft, no matter which shaft you use in this range and which hole you use in this range, the hole is always larger, and that guarantees a clearance fit. Let's take a look at the next one. Okay, so in this case, if we were to round off, we would have a basic size of 0.75, 3/4 or 3/4 diameter. Okay, so in this case, if we take a look at the shaft, take a look at the hole is always smaller no matter what. So no matter what shaft you pick from this range and which hole you pick from this range, which hole diameter you pick, the shaft is always larger than the hole, guaranteeing interference. The hole is always smaller no matter what. So you're going to have to force that shaft into that hole. the clearance will always be negative, whether it's maximum or minimum. It will always be negative, guaranteeing interference. Okay, let's take a look at the next one. Okay, obviously for the next one, we're looking at 3/8 or 0.375 for our fraction. That's what we're aiming for. Okay, so if you look at the shaft, 0.373 up to 0.378, and the hole, 0.371 up to 0.375. So if you were to randomly pick a shaft from the bucket, you're going to end up with one of these diameters and everything in between. Same thing with the hole. If you were to randomly pick one of the holes, you're going to end up with anything from 371 up to 375. So in this case, the hole may be smaller than the shaft. Or the other way around, you may end up with a shaft that's larger than the hole. So here you're going to end up with a positive for your max clearance and a negative for your minimum. So in this case, we're going to end up with a transition. Okay, and for the last one, obviously we're looking at 1/4 or 0.25 for our basic size. So in this case, we may end up with the perfect match. If we randomly pick a hole, we end up with 250, and we end up with the shaft of 250. That's a perfect match. So we may end up with the perfect match, or we may end up with the shaft that's slightly smaller than the hole. So this is a inline fit or line fit. Hand to a glove, either it's going to be a perfect match or the hole would just be slightly larger than the shaft. So let's go back. Quick review. Clearance tells us that the hole will always be larger than the shaft. There will always be space, so that's clearance. Interference tells us that the hole will always be smaller than the shaft, so you have to force the shaft into the hole, either with a hammer or a press to force it in there, and friction will hold it in place. Transition, you may end up with a large hole or a small hole with respect to the shaft. So that's transition. That means you'll get a positive maximum clearance and a negative minimum clearance. And once again, inline is a perfect match or a little bit of space between the shaft and the hole, just like a hand to a glove. Either it's a perfect match or the glove is just slightly larger than the hand. Next slide. So we're going to also be doing this on your handout for today, for this lecture. We're going to be calculating tolerance and basic size. So let's take a look at the shaft. So the shaft can be anywhere from 2.1 up to 2.2 in diameter. And the hole can be anywhere from 1.8 up to 2.0 in diameter. So what is the basic size? If you were to round this off, the basic size would be 2. That's the diameter we're aiming for, but because of the tolerances, we get 2.2, 2.1, or something under 2.0, down to 1.8. But a nice round number is 2. Now the tolerance is just the difference. So the maximum diameter minus the smallest diameter allowed, that'll give us 0.1. Once again, subtract 2.1 from 2.2. That's the tolerance for the shaft. That's the wiggle room for the shaft. The wiggle room for the hole is just 2.0 minus 1.8, and that'll give us a tolerance of 0.2 for the hole. Next slide. Okay, so part of your assignment also for this chapter will be to define the relationship between the hole and the shaft. You're either going to end up with a clearance, transition, interference, or inline fit. Okay, so to be able to define your relationship, you're going to have to do some math. You're going to have to calculate the maximum clearance and the minimum clearance. Okay, so to do the maximum clearance, from the previous slide, we learned that you take the largest hole minus the smallest shaft diameter allowed. Okay, so the largest hole allowed is 2.0 diameter, so it's 2.0. And we're going to subtract the smallest shaft allowed. So the smallest shaft allowed is 2.1. And we're going to end up with a negative 0.1. Negative 0.1 for our maximum. Now let's calculate our minimum. Okay, so our minimum is going to be small hole minus large shaft. Okay, so let's take a look at the small hole. The smallest hole allowed is 1.8, so 1.8. And we're going to subtract the largest diameter allowed for the shaft, which is 2.2. Okay, and we're going to end up with the negative of 0.4. So if you notice, we ended up with a negative maximum clearance and a negative minimum clearance. So we ended up with two negatives. When we end up with two negatives, negative for the max, negative for the minimum, then that always guarantees interference. Okay, so interference will be our relationship. The hole is always smaller than the shaft. Next slide. Identify the type of fit and the system used to determine the limits of the following shaft and hole pairs. Okay, so let's take a look at the first one. Let's take a look at the shaft. So the shaft, so if you have a bucket of shafts, let's say you have 100 of them, and they all meet the tolerance anywhere from 9.972 in diameter up to 9.987 in diameter. And let's say this is millimeters. And then we have a bucket of blocks, each one with a hole. And the hole can range anywhere from 10 up to 10.022 in millimeters for our diameter. So what type of fit do we have? So the type of fit is it clearance, interference, transition, or inline? So here we can see the hole is always larger than the shaft. So we're always going to have clearance. We're always going to have a positive for the max and a positive for the minimum clearance. So that'll give us a clearance fit. And once again, the hole is always larger than the shaft, always guaranteeing a clearance between the shaft and the hole. Okay, let's take a look at the next one. So the second one, we have a bucket of shafts ranging from 60.002 up to 60.021 in diameter. And in the other bucket, we have blocks with holes ranging from anywhere from 60 up to 60.030. Now, if you randomly pick a shaft and randomly pick a block with a hole, what type of relationship are you going to have? You're either going to end up with a hole that's smaller than the shaft, or the other way around. You may end up with a shaft that's larger, a hole that's larger than the shaft. So you're going to end up with the mix of either space or no space. So you're going to end up with a positive clearance and a negative clearance for the minimum. So this is going to give us a transition, meaning the hole may end up being larger or smaller than the shaft when you randomly pick from the buckets. Okay, let's take a look at the next one. So here we have a shaft of 39.984 up to 40. So if you randomly pick a shaft from the bucket, you may end up with something as small as 39.984 or something as large as 40.000. And in the other bucket, we have the blocks with holes. The holes range from 39.924 up to 39.949. So in this case, the hole is always guaranteed to be smaller than the shaft. No matter which block you pick, the hole will always be smaller than the shaft. The largest hole we can pick is 39.949. The smallest shaft is 39.984, which is larger than the hole. So the shaft is always guaranteed to be larger than the hole. So that'll give us an interference, meaning the maximum clearance will be negative, the minimum will also be negative, and that'll be an interference, guaranteeing the shaft is always larger. Okay, this is not covered in your assignment, but it's an important topic. You're going to hear tolerance stack up a lot in manufacturing, assemblies. Once you start bolting things together and there's a tolerance stack up, you may end up with a part that's either too large or too small for the assembly. Okay, so here they're asking us to take the tolerance accumulation between datum A and B. So this is datum A, datum B. So if we take plus or minus 0.1, plus or minus 0.1, plus or minus 0.1, combine them, that'll give us a tolerance of plus or minus 0.3 with the total dimension of 70, which is 20 plus 30 plus 20 is 70. This is not a good way to dimension an object, this continuous chain dimensioning. Next slide. So once again, we get the 70 by combining the 20, 30, 20. If we had, again, a perfect part with no tolerance, so 20 plus or minus 0, 30 plus or minus 0, 20 plus or minus 0, that would be a perfect part, which doesn't exist. And that would give us a perfect length of 70. Again, under perfect conditions, perfect environment, this we would be able to achieve, but it's impossible to achieve a perfect part. The higher the tighter the tolerance, the more perfect or accurate you want the part, the more expensive it gets, and the machine shop will charge you a lot more money to go slow to try and achieve perfection. So if you go with the maximum tolerance of plus 0.1, you'll end up with 20.1 plus 30.1 plus 20.1. This is the worst case on the maximum side. Add them all up, you get 70.3 on the maximum. Worst case on the minimum, which is 20 minus 0.1, 30 minus 0.1, 20 minus 0.1. The worst case, the minimum size we'll get is 69.7. From one of the previous chapters, we learned to pick a large surface as our datum. So obviously this has the largest surface. And dimension from there. So we can dimension to our first step, from the datum to the first step, then datum to the second step, datum to the third step, and finally datum to the final step. So if we wanted to know the accumulated tolerance between surface A and surface B, all we have to do is take 40 plus or minus 0.01 and subtract it from 110 plus or minus 0.1. What would be the tolerance? Well, 110 minus 40 is 70, and the combined tolerance is plus or minus 0.2, giving us a more accurate dimension than the previous form of dimensioning if you would have gone with chain dimensioning. Now in a perfect world, if we could create the perfect part with no tolerance, 40 plus or minus 0, 60 plus or minus 0, 90 plus or minus 0, 110 plus or minus 0, then we would get a perfect length of 70 between surface A and B. These are under perfect conditions, but there is no such thing as a perfect world. You always have to provide some tolerance. The tighter the tolerance, the more perfect you want to make the part, the more the machine shop is going to charge you because they have to go slower to achieve that close to perfection condition. And in the worst case with the minimum, we would have 39.9 for our minimum, 40.1 for our maximum. That was the plus or minus 0.1. Same thing with this dimension, plus or minus 0.1, we would get 110.1, 109.9 for the minimum. So if we were to take the minimum, the worst case, subtract them, we would get 69.8. Now, if the dimension between surface A and surface B was more important than with respect to the datum, so instead of having the long dimension from the datum to surface B, if this dimension was critical, then we would break from dimensioning from the datum and directly put a dimension from surface A to surface B, giving us a more accurate dimension, a tighter tolerance of plus or minus 0.1. And again, if the accuracy of the distance between A and B is important, maybe a part that mates to it, its opposite, has to make contact with both datum A and B, then the best way to dimension it is as shown on the previous slide. Dimension straight from surface A to surface B, instead of dimensioning from the large datum to surface B. By dimensioning straight from surface A to surface B, we get a more accurate part, and it can now correctly or more accurately mate with its opposite. Okay, let's take a look at this example. This is not covered in your homework, but it's good practice for dimensioning correctly. Assuming that the diameter dimensions are correct, explain why this object is dimensioned incorrectly. Let's go ahead and take a look at the mistakes. So first of all, the decimal places don't match, and this will be covered in the next chapter. If you show 3 decimal places for the basic dimension, then you must also show 3 decimal places in the tolerance. Okay, same thing with this one. Another thing that's incorrect is you'll see that if you were to do the math and add these two dimensions, it would not match this dimension. In other words, we're double dimensioning. One of these has to go away. So if this dimension is more important, you keep this one. If this is more important, then you keep this one. If you're not sure which of the two to keep, then you keep the one that's dimensioning to our large surface, our datum. And as mentioned in the earlier slide, if you have 3 decimal places in the basic dimension, you also need 3 decimal places in the tolerance. So you can see here this is incorrect. 3 decimal places, then this should also have 3 decimal places. This is correct, 3 decimal places, 3 decimal places. Not correct. This is only showing 2 decimal places, so this should show 2 decimal places also. The basic dimension and the plus and minus values should have the same number of decimal places. Same for limits. You have your max and minimum limit. They should also have the same number of decimal places. Here's the incorrect way. This has 3 and this one only has 2. They have to match as shown on the left. Both values should have the same number of decimal places. And also with your basic dimension with your plus or minus, you should also have the same number of decimal places, 3 and 3. Here, if you only have 1 decimal place, then this side should only show 1 decimal place. The number of decimal places in the basic dimension should match the number of decimal places in the tolerance. And same for angular tolerance. If it has 1 decimal place, the tolerance should also have 1 decimal place. Both the angle and the plus and minus values have the same number of decimal places. And just a quick review, to calculate maximum clearance, you take the large hole minus the little shaft. Minimum clearance is little hole minus the large shaft. If you end up with 2 positives, positive max, positive min, then it's clearance. If you end up with the positive max, negative minimum, then it's a transition. If you end up with a negative maximum, negative minimum, and it's interference, meaning the hole is always smaller. And an inline or line fit is when you have a positive clearance and a 0 minimum clearance, meaning the diameters are equal. Okay, this is like a glove to a hand, perfect match. End of lecture. All right, for your assignment, let me just go over the first problem from the back of chapter 13, problem 13-1, and there will be 8 parts to this 13-1. Let's go over the first one, problem 13-1A. All right, so we have a shaft that has a diameter from 0.9975. It can be down as low as 0.9963 in diameter. And there's a hole in a block. The hole has a diameter of somewhere from 1 inch up to 1.002 inches. Okay, so basic size. So basic size is a nice round number or a very common fraction that you would see on a ruler. So in this case, it's obvious that 1 is our basic size. Now the tolerance for the shaft, okay, so again, think of tolerance as a wiggle room. Okay, so the shaft, it's around a 1-inch diameter. It's actually slightly smaller. So what is the tolerance? What is the total wiggle room you have? It's just 0.9975 minus 0.9963, and that'll give us 0.0012. You do take the absolute value, meaning you don't use a negative for the tolerance. And for the hole in the block, our tolerance, our wiggle room, is just 1 subtracted from 1.002. And the tolerance or wiggle room is 0.002. Okay, so, and we use absolute value, meaning no negatives for the tolerance. All right, for maximum material condition. So in other words, the shaft, so if we look at the shaft, maximum material condition, it's when it's at its heaviest. That's when we have the largest diameter. So the larger diameter shaft allowed is heavier than the smaller diameter. So our MMC, maximum material condition, is at 0.9975 in diameter, inches. Now, the heaviest block will have the smallest hole. The smallest hole allowed is 1 inch. The largest is 1.002. So the smaller hole will remove less material. When we drill a 1-inch diameter hole in the block, that'll give us the heaviest block, the one with the small diameter of 1 inch. Now, least material condition is when the object is at its lightest, right? Least material condition. So the shaft is at its lightest when it has the smaller diameter of 0.9963. Okay, so least material condition for the shaft, small diameter, 0.9963 inches in diameter. Now for the block with the hole is when you have the larger hole. So the larger the hole, the more material you remove, the lighter the block. Okay, so the least material condition for the block is when you drill the larger hole, you're removing the most material allowed, which is 1.002 inches in diameter. All right, and maximum clearance. So from the previous slides, we learned that maximum clearance is when you have the largest hole minus the smallest shaft. Okay, so for maximum clearance, we go to the largest hole, 1.002, and you subtract the smallest shaft allowed, and that'll give us 1.002 minus 0.9963 will give us a maximum clearance, positive 0.0057. Now for the minimum clearance, it's the smallest hole allowed, which is 1, minus the largest shaft allowed. So we take 1, subtract 0.9975, and we get positive 0.0025. And for the tight fit, if you get 2 positives, so we got 2 positives, that means we will always have clearance, meaning the hole will always be larger than the shaft. All right, so do the same thing for the rest of problem 13-1. It goes up from A all the way up to problem H. All right, so good luck with the homework.